So hi and welcome to the weekly Science Hour on CosmoQuest. I'm Emily Lakdawalla from the Planetary Society. And ordinarily in the Science Hour, we have a scientist or engineer guest to talk to you about their work. But this week, I decided to present the expert as me because I've been tuned into Curiosity for a really long time now. And I know that people are very curious about what this gigantic rover is doing on Mars. With me today is Fraser Kane from Universe Today, who is greatly facilitating this hangout, as it's been a while since I've conducted my own. So I'm grateful, Fraser, for your assistance helping me out today.
No
And I
problem.
guess,
It feels really weird to not be the one introducing everybody. I like it. This is good.
good. All right. Well, I thought I might start with just a quick recap of what's happened so far and what we have to look forward to. Curiosity, of course, landed on Mars late on Sunday night, my time, about a little more than a week ago. We are now in Sol 9, actually probably just about turning over the clock into Sol 10, the rover's 10th full day on Mars. It landed on Sol 0. Interesting thing about that is that not every Mars-landed mission has used Sol 0 as the landing day. Programmers like that convention. Most ordinary people who are not programmers don't usually think about things starting at 0. So some missions have used Sol 1. I think Spirit and Opportunity used Sol 1, if I'm not mistaken, for the landing day. But for Curiosity, it was Sol 0. They did some initial checkouts of their cameras on Sols 1, 2, and 3. They got the mast up. They took a beautiful black and white panorama with the nav cams, which are wide angle cameras that are used to scope out the landscape and figure out the shape of the landscape where they are. They're navigational cameras. On Sol 3, they took a full color panorama with their mast cam 34, the medium resolution mast cam. If you've ever looked at a picture of Curiosity, you'll notice that its two eyes are different sizes. That's because one of the the left camera has a 34 millimeter focal length, and that's sort of a medium angle view. Takes about 130 pictures to make a full scale 360 degree panorama. Then there's the Mastcam 100 with a 100 millimeter focal length, and that is really a telephoto zoom lens. And they probably won't be taking full panoramas with that one. They'll be using that to kind of sight, it's like a telescope sighting things at a distance and trying to figure out where to go next. They have so far not taken very many pictures with Mastcam 100. They spent the next 4 sols doing what's been called a brain transplant. It's more like an operating system upgrade where they already had the new OS loaded into the rover's memory, but it wasn't what was actually operating the rover. They were operating the rover with software that was designed to help it cruise to Mars, to act like a spaceship, and they needed to replace it with an operating system that was designed for the rover to be a landed rover that moves about and has an arm and science instruments on Mars. And the modules for that are quite different to what it needed while it was a cruising spacecraft. So that's why they had to stop a few days after landing and replace their operating system with this new one. It took them 4 days because Curiosity has 2 complete redundant computer systems. And so they spent 1 day loading it into computer number 1, the second day using computer number 2 to test computer number 1 to make sure everything was okay. And then they did the same with the other computer. So that's why it took 4 complete days on Mars. But that went very well. It finished up at the end of Sol 8, and probably on Sol 9 they started doing some more of their instrument commissioning. That was today. I haven't heard anything about how Sol 9 went yet, but I'm hoping that we'll get some more updates from Curiosity tomorrow. What we have to look forward to for the next several weeks is a very slow process of getting the rover ready for science operations. This is the most complex machine that has ever been landed on another planet. And when you have something this complex, it takes a long time to get it ready to work. So they're proceeding very slowly, running each of the instruments first through basic electrical tests. Can we turn it on? Does electricity run through its wires? And then slowly increasing the sophistication of the tests, like with the APXS elemental measuring tool. They first ran it for just a couple of minutes, then they ran it for 15 minutes to see if the signal to noise ratio improved, and so on. So they're going to spend the next week doing commissioning of the remote sensing instruments. Those are things like the cameras, the ChemCam, which is the laser beam on this robot's head that it can use to turn rock into plasma and then see what the elemental composition of that plasma is. And they will also do their very first driving test this week. On Sol 13, the very first thing they'll do to move the rover is just to swivel the wheels back and forth, make sure their steering actuators work right. So we'll get to look for HazCam images of the wheels turning this way and that way. And then 2 sols later, they'll do their first drive. And they think that probably what that will be is to drive several meters forward, because they've seen the landscape right in front of them, and it looks perfectly benign, quite flat, at least for the first few meters. And then they'll drive several meters backward to try to get on top of where they were when they landed. And again, these are just initial tests to make sure everything is working correctly before they start driving off across Mars.
I think the most important thing is those are on the wheels. It's got the it does Morse code for what NASA JPL. So as they roll, they'll actually imprint that NASA JPL on the surface of Mars.
That's right. And of course, that's not just, as much as JPL likes leaving literal imprint everywhere they go. That wasn't just for vanity's sake. There's a reason for that. Having those little having a slight change in the tire tread pattern as they go along makes it a lot easier to count where how far they've gone looking at either from space or using the rover's navigational cameras. It makes it a lot easier to match up images taken by the rover of its tracks with the images that are taken from orbit of the rover's tracks behind it.
Which is kind of mind-bending when you think about it. I mean, the fact that a spacecraft from orbit is going to be looking down at the tracks, and they're going to be able to pick out the differentiation of the tracks to know sort of how many wheels have turned. Like, yeah, if anyone is considering that they're faking images, they're out of their mind at this point.
It's really pretty spectacular what HiRISE can accomplish, and it's kind of hard to remember that Spirit and Opportunity did not have that at the start. Mars Reconnaissance Orbiter arrived in 2005, more than a year after Spirit and Opportunity landed on Mars. And so in the beginning, Spirit and Opportunity, the only way they could navigate through their landscape was using their navigational cameras to pick out a future path, because the images that we had from orbit were enough for sort of a basic idea of where we want to go, but you could not plan rover traverses because they just weren't high enough resolution. Now, with Mars Reconnaissance Orbiter HiRISE, you can see every rock on the ground that is as big as a rover wheel. Every single one. You can count them. Graduate students have counted them, which is, sad task for probably an undergrad these days. They're given that kind of more menial task. But anyway, we know exactly where every hazard is that this rover could possibly encounter, and that's really going to speed up the decisions that are made about where the rover should go. Now, it won't make the rover actually get anywhere any faster because the rover's top driving speed is quite similar to that of Spirit and Opportunity. And even though it may take rather long traverses, it's also going to be stopping for a much longer period of time at each science stop, because it's going to take a really long time to get samples acquired, prepared, documented, put into the sample analysis tools inside the rover. And so each science stop is going to be a several-week period.
Now, and we should probably let people know how they can start preparing their questions while they're listening. So, sorry to interject, which is that if you want to ask some questions to Emily, and I will attempt to sort of stay on top of this, which is there's a bunch of places you can do that. You can post any questions that you want if you're watching this on the YouTube video, so there's a place where all the live questions are showing up. We'll be watching those. You can also, if you're watching this on Google+, in Emily's chat, in one of her posts, you can post your questions there. If you're watching this somewhere embedded, for example, watching this embedded on Emily's blog post on the Planetary Society, you can post a question on Twitter, and we'll be able to see that as well. Just use the hashtag CQX. And we'll be able to respond to that question and fire those off to Emily. So, and I know I can see a bunch of questions packing up, but I just wanted to make sure that people knew how they could ask those questions. So, and we'll attempt to sort of stay on top of the questions as they come in.
Yeah, and I'm going to try. I'll probably do another 5 or 10 more minutes of chatter about what we'll look ahead to. But I want most of this to be questions and answers, so we can get to those pretty soon. Yeah,
and if people don't have questions, I got a million, so it'll be great.
Excellent. All right, so anyway, we're getting a little bit ahead of ourselves talking about driving, because it's actually going to be a while. We need to be extremely patient with this mission. That they'll finish the commissioning of the remote sensing instruments in about a week. Then they have a period that's called intermission, which is when the scientists are allowed to do some stuff with the rover before they get into their next commissioning period. And it's rumored that probably what they will do is they will drive to a new site at that point. I don't know how far they'll drive. I'm wondering if they're willing to drive drive as far as the high thermal inertia unit, which I will talk about in a minute what the heck that means. They may not be able to drive that far, but they'll drive to a site where they are going to be interested in using their in situ instruments, the ones at the end of the arm, to do their first sampling. And so after intermission, there's going to be another week or two where they commission all of those arm-mounted instruments. And that'll actually be kind of a fun period because they'll unstow the arm for the first time. We'll see probably some video of the arm moving around, which will be great. They'll have to investigate each tool on the arm, so they'll like point each tool, they'll rotate it, they'll take more pictures of that tool, they'll rotate it, take more pictures of this tool, and hopefully during that period, I don't know, this is my guess that they'll do it, but there's a camera on the end of the arm. The camera's called MAHLI. It stands for Mars Hand Lens Imager, but it's so much more than a microscopic imager. It's actually got a quite wide angle field of view, and it's in color, so it should be able to point the camera at itself and take its own picture, get like a nice profile photo, like one of your cell phone
holding your
yeah, just
cell
like
phone
that.
out and looking.
It's going to be just like that. It's going to be really awesome. So I hope that they do that in that period, although I'm not sure if they're going to. And so that will take a couple of weeks, and then once they've done that, they have to go through what's called a senior review, and that's where they present what they've done so far to people above their heads, above the mission at JPL and NASA, and have to prove to them that they've gotten this rover ready for operation before they can acquire their very first sample of soil and put it inside those laboratory instruments inside the belly of the rover. And so all of this whole process, it's gonna be about 2 months before we do any significant amount of driving. But what we have to look forward to when we start driving is pretty exciting. So I'm going to just give a little bit of preview of where we're going. I'm looking around because I'm going to whoops, not that one, screen share. There we go. Okay, so what we have here is a mosaic of images taken by the Mars Reconnaissance Orbiter context camera. It's one that you don't hear about very often, but it's probably one of the most I think undervalued cameras in operation right now. It is a spectacular instrument that takes very wide field, very large number of pixel swath images across Mars. The resolution's lower than HiRISE. It gets about 6 meters per pixel, but it covers huge areas. And in fact, over the course of the Mars Reconnaissance Orbiter mission, they've actually covered nearly all of Mars with this camera. So this is the northwestern part of Gale Crater. The rover landed right about in here, and this down here is the mound, which is variously called Aeolus Mons if you like the IAU, or Mount Sharp if you don't. And the mound is where they really want to go. They had to land up here because it was flat and fairly safe for the rover to land on, but they want to get down here where these interesting looking rocks are. And I'm going to zoom in a little bit. In order to get down there, they're going to have to cross this dune field first. These are black sand dunes. You can see they have beautiful crescent shapes. They're called Barchan dunes. And they're made of this black basaltic sand that probably came in from outside the crater entirely. And the rover does not want to drive on these dunes. It is not safe for it to try to traverse these steep slopes of very loose sand. So they're going to take a course that they'll have to go south from their landing site, but then go southwest for a while until they get to this gap over here, where they're going to be able to drive in between some sort of more isolated dunes in order to get around them and get up to this area, which is where the interesting stuff is. Down here, there's two particular kinds of rock that Curiosity is looking for. They formed in different periods of Mars's history. Where my cursor is right now are clay-rich sediments. Clays form when you have water interacting with rock, where you have a lot of water over a long period of time at a fairly neutral pH. Up higher than that, you get to a different kind of rock called sulfates. Sulfates form when you have much more acidic water in contact with the rock. And those are the kinds of rocks that Opportunity has largely been seeing at its landing site, which is just about 1,000 kilometers to the west of here. And those two different kinds of rock come from different eras in Mars's geologic history. The clay-rich stuff probably formed during a time when Mars was a bit more benign than it is now. The sulfate-rich rock formed at a time when the Tharsis volcanoes were belching out huge quantities of sulfur dioxide gas, acidifying the atmosphere and generally making it a not very nice place to live. So since the Curiosity mission is all about looking for habitable environments on Mars, it's really interested in these clays, but also interested in the transition from the clay period to the sulfate period. I'm going to scroll down a little bit here just to show you what we have to look forward to. After it investigates these clay areas and these sulfate areas, it's going to start climbing, we think. This is sort of a notional traverse. They may change their minds, but it's what they've been talking about. And they'll go up here in this channel, and you can see that there's these beautiful layers in this rock channel, and these buttes and mesas. And those buttes and mesas are what you see on the flank of the hill in the very first color panorama that we got down from Opportunity. We got down from Curiosity. When Curiosity starts driving up through this, the landscape photos are just going to be absolutely tremendous. I cannot wait for that phase of the mission. One more picture I want to show you is a very high resolution view taken on Sol 6, I think. You can see Curiosity sitting here on the surface. You can see the sort of bluish grayish areas where the landing jets impinged on the surface. You can even see two little sprays this way because the descent stage, the rocket jetpack, when it disconnected from the rover, it tilted and flew off in this direction. And so you can see where the jets sort of were thrusting against the surface as it flew off in that direction. We go south and you can see the generally flat terrain immediately to the south. You go a little farther south and you see it starts getting this blue color. That blue color tends to be less dusty, more rocky, and the reason that it's less dusty and more rocky is because of these sand dunes. They're made of very coarse sand. They're actually moving right now. The wind is blowing them across the surface, and as it blows this sand across the surface, it's scouring the bedrock and removing the dust, so we actually have much more rock exposed down here. But again, these are that part of the sand dunes that Curiosity does not want to climb up. That would be very bad news. So you have to get across and around this dune field, which is really very beautiful. And then you can see these more clay-rich rocks on the southern side of the dune field, which is what it's really going to be going there to investigate. So it's a very exciting mission we have to look forward to, but we also have to be extremely patient as we wait for them to get started with the scientific part of the mission. So I think that's all the lecturing I'm going to do at this point. I'm very happy to throw it open to questions.
Okay, well, it's a bunch of questions we've got right now. So let's see. Why don't we start in opposite order right now while I get organized. So Sam Gunn asks, why is it taking so long to move MSL as opposed to Sojourner and Spirit and Opportunity, which were quite fast off the mark?
Just because it's so complicated. Although you have to remember that Spirit and Opportunity, by this point in their missions, neither one of them had left their landers either.
Yeah, I don't recall them being that quick off the mark either.
No, it took about 2 weeks for each one to get off their landers. They were very cautious in that step because there was actually a lot of hazards represented by sitting on top of that lander, ways that you could foul wheels or do whatever, or get airbag material entrained in the wheels. So they had to be extremely careful as they were exiting their landers. And as a matter of fact, they were not off the landers by this point in the mission. So technically, yeah. Curiosity had 6 wheels on soil before any other past rover has, because it did it right on Sol 0. Can't beat that.
And we're just a couple of days away now for the wheels actually starting to turn.
That's right. So they say Sol 15 is the first day that we should really see a drive. And of course, all of these Sol numbers that I'm giving are assuming everything continues to go well. Everything's gone very well so far. But if they encounter even the slightest problem, they'll slow down. This mission is intended to last an entire Mars year, which is 687 Earth days. You compare that to Spirit and Opportunity, which were their nominal missions were 90 days long. I realize that Opportunity has lasted a lot longer than that, but at this time in the mission, they were thinking our mission may only last for 90 days. Sojourner was only supposed to last for 8 days. And it lasted, I think, 83. So JPL has a good record of long-lived missions, and let's hope that Curiosity follows that. Although I really don't think that we can hope for it to last 10 or even 20 times as long as its nominal mission, which is what they've done in the past. This one will not be that long, but it will be a good long time.
Right, but they thought that the lifetime of Spirit and Opportunity were set by the amount of dust that was going to accumulate on the solar panels. And when they realized that dust devils were coming along and cleaning off those solar panels, it almost pushed the lifetime of them to the point that they just started to mechanically break down, which Spirit has broken down. Opportunity's had its share of issues. But in this case, the thermal reactor that's in Curiosity, it's going to last for years and years and years. It's probably going to be mechanical breakdown that brings this. So it's not like it's got that. I mean, they were sure when they first launched Spirit and Opportunity that really that solar power degradation was going to shut those missions down.
Right. And with Curiosity, of course, they know exactly the profile of the power degeneration that they're going to get from the radioisotope thermoelectric generator, or RTG. It, I think, is going to provide enough power to continue operating everything without much difficulty for about 14 years. And as with past missions, they can get quite clever about things that they slowly turn off in order to conserve their power requirements, just like they're doing with Voyager now, where, the Voyagers are so far past their intended operational lifetimes, and they're living on just a trickle of power from their RTGs. They'll probably run out of power now in 2020, but they were only really supposed to last for a few years. So they'll probably do the same to eke power out of Curiosity. With Opportunity, one of the things that they had to do is they had to sacrifice the mini test instrument because they couldn't keep its heater on overnight, and that as a way to conserve power. And so they'll make those kinds of hard decisions if we are so fortunate as to have Curiosity still alive in 14 years.
Okay, so here's a question on YouTube from Nornek. Will Molly be able to see bacterium if they existed on Mars and get done with the life questions? So, I mean, I know we've been banging the drum that that Curiosity is not designed to search for current or past life on Mars, that it's looking for the possible environments that life could live on Mars, could have existed on Mars. But if there was like colonies of past bacteria, fossilized bacteria, would it be able to detect it?
I don't think so. I don't think its resolution is sufficient. I believe, off the top of my head, I think that its highest resolution is 14 microns per pixel, which is very, very small, but it's not enough. It's not technically microscopic. Just a couple of those things together, and you've got a grain of sand that you can see. So really, it's designed to look at sand-sized grains in rocks. And so it's designed to look for rock textures, and those rock textures are clues to the paleo environment that existed at the time when those rocks formed. But it's most definitely not designed to look for unicellular organisms or anything else that existed on that scale.
Right. Definitely a big old dinosaur bone on the surface of Mars.
Yeah,
so
sure.
Spot that.
Absolutely.
Which is what the scientists told us. We're like, if there's a dinosaur bone there, we will absolutely see it.
Yeah, and they will absolutely tell you, because let me tell you, one thing that would jumpstart Mars funding would be to know that there were fossils there. So believe me, if they see something, they're going to tell us.
Well, and what's great about this mission, and a lot of the NASA missions as well, and you kind of gave us all a schooling on this, is how quickly they release these images to the public without any kind of filter at all. They just take these images, they dump them on their servers, and then they study them as quickly as we do. I know in many cases, during the landing, I think Jason had the nicest image of some of the camera footage from the landing faster than NASA had it put together, because he just went right to the raw images and put them together.
Yeah, and actually I've given a couple of talks recently at NASA headquarters and the Applied Physics Labs trying to exhort these people to take advantage of the image processing skills that are out here in the amateur community. Scientists have one thing in mind when they process images. They're looking for scientific results. So there's and that is different from making pretty pictures in a couple of ways. One is that scientists do not like changing the data any more than they absolutely have to. So they're not going to they're not going to carefully blend seams together to make seamless looking mosaics, because that's falsifying the data in a way. So you won't see a lot of really perfect mosaics. You'll always see mosaics that have little seams in them when they put all these image frames together, because they don't want to alter the images by painting things out. And actually the Chinese ran into a problem with that on their lunar mission, Chang'e 1, where they had put together a couple of adjacent images, and they did blend the seams to make them disappear. And what they didn't realize when they had done that is that they had cloned a crater, and they actually went out with a press release saying, we discovered a new crater on the moon. And it was because of what they had done to try to make the image look prettier. So you really don't want scientists doing this kind of manipulation, because in a sense, it's making up information that wasn't there before. However, you really want to do it when you want to make pretty illustrations. And as long as you keep those worlds apart, one type of image processing for science work, another type of image processing for illustration, then I think you're safe. And I think it'd be wonderful if NASA would take more advantage of the skill that's out there in the amateur community to process and make these pictures look pretty.
Yeah, and I think they, actually, you know what? I'm not going to continue this conversation. We're going to get to some more questions. I could go on all day.
Yeah.
So Carolyn McCardle asks, are they looking for some geological features that suggest there could have been past life on Mars, or are they looking for things in the soil that would make life possible now?
Neither, actually. So it's sort of a complex, nuanced mission that they have. Previous missions were sent to Mars to look for evidence that there was long-lived water at the surface. NASA's mantra at the time was follow the water. We know there is water on Mars right now. You can see it with a telescope. You point a telescope at Mars, you see it has ice caps. Okay, so there's water on Mars, but it's in a form, ice, that's not usable by life. So we sent spacecraft and rovers to look for places where there might have been liquid water lasting for a while. And both orbiters and the rovers have found good evidence supporting the conclusion that yes, there were places where liquid water persisted for at least some period of time. So the next step in this process, which ultimately is leading to the search for life, but it's not yet the search for life, the next step in this process is to look at one of those environments that definitely once had liquid water and try to understand if that environment is one in which life really could have existed, and if it did, if it could have been, if evidence for it could have been preserved. So they're looking not just for evidence of watery environments that we know already existed, and Curiosity is specifically sent to study these clay and sulfate rocks that required liquid water to form. But you need two other things for life. You need a source of energy, and you need organic material to build the life from. Now, we know that Mars gets both of those things. It gets energy from the sun. It, at one time, had energy from its internal geology, just like Earth does. And it also gets a lot of organic material delivered by asteroids, just as Earth does. So Curiosity is going to be looking in these watery environments to see if that organic material survived in these watery environments, to see if we can find these carbon-rich chemicals still there, if they're preserved in the rocks. And it will be doing some basic stuff like isotopic analysis to see if there's anything unusual in those isotopic ratios. To try to answer this question of whether Mars once had habitable environments. The nice thing about this particular mission is that even if Curiosity's conclusion is that no, these things weren't habitable, we still will have learned a great deal about Mars's geologic history. And that makes it very different from the Viking landers, because the Viking landers were sent to Mars to discover life. And they didn't, or at least they didn't discover evidence for life that everybody agrees upon is evidence for life. There are a couple people who still think that they may have, but I think the vast majority of the community either thinks that they didn't find anything or that the results are equivocal. So and so they've broken it down into these much smaller steps, and Curiosity is looking for this: could life have existed there? Are there environments favorable for it? And if so, were they preserved where we can find them? It would be followed on by a mission that would go retrieve a sample from a kind of rock that is most likely to preserve evidence for this kind of habitable environment in the past.
So I guess imagine you've got some of the scientists and they're looking at some of the data coming back from Mars, and they're checking off a list of the things that meet their criteria. So they're going to look for some kind of mineral that appears with the presence of water. They're going to be looking for something else that maybe appears with the presence of organic material, and perhaps something that can demonstrate that there was a source of energy, so something that was interacted by sunlight or thermal heat from the interior of Mars. So, and try to see all three of those things in the same location. Is that
sort of
like that?
Sort of, and then there's the temporal element too. So it's fine to have all of these things, but if it only existed for a few hours on one particular day in Mars's history, that's not going to do life any good. You have to look at the history as preserved in a very long sequence of rocks and see if those kind of environments were common or rare, and whether they were persistent for long periods of time, whether year over year you might have had a lake in this crater, or whether it was just like a flash flood and then it dried up and it was gone. And that's actually one of the reasons why they eliminated one of the other more exciting landing sites. There's this place called Eberswalde Crater that had this absolutely stunningly beautiful river delta formation in it, which would be perfect for both the existence of and preservation of organic material. But you can't really tell if the thing formed in just one flash flood or just a series of flash floods over maybe 1,000 years of Mars's history, or if it was 100 million years. It's just impossible to tell. And so that temporal element is also a really important part of the story. And that's one of the things that we really have not answered yet. We've seen some of these kinds of rocks that formed in watery environments, but we really don't know yet whether they were persistent or not.
But as a geologist, I mean, you can see places like that here on Earth. that you can scrape away the, some layer of an ancient lake bed or seabed and see a place, and that's clearly all of the pieces of the puzzle were there as required.
You can in relatively recent rocks, but this search is actually extremely difficult in rocks that are the same age as the rocks that we're having to look at on Mars. There's a couple of geologists on the Curiosity mission whose specialty really is in looking for life in ancient Earth rocks. And they tell me that, if you happen to find a fossil in a 3.5 billion year old rock, that's your PhD right there. You don't have to do anything more, basically. You write that up, you've got a PhD. It's really rare. It's very difficult to do even on Earth, which is why they haven't set the goal of looking for actual life, because if you sent a rover to do that on Earth, you probably wouldn't succeed, much less on a place where life may not have existed at all. So they're really focused more on this, understanding the geologic history of this very ancient period in Mars's history. We're talking about 3.8 billion years ago. It was a really long time ago.
All right, let's take some more questions here. So a space colonizer wants to know, does the laser have any redundancies? So if the laser breaks, are there more sort of spare parts?
That's a good question. I think that for the science instruments, there isn't a lot of redundancy. There are, the sampling, probably most of the redundancy is in the sampling tools. Excuse me, so like the drill mechanism, there are actually 2 replacement drill bits mounted on front of the rover, so that if the drill gets stuck in the rock, it can actually release the bit and go get one of the other 2 drill bits. And the sampling tools, they have a number of chambers which are all reusable, so you can presume they'll probably slowly get contaminated over time, but at least those are all reusable, so if one of them breaks, you'll be okay. But with the science instruments, there's not a lot of redundancy. So yeah, if the laser breaks, then you don't have a laser anymore. And it's really difficult to have redundancy on the science instruments just because they're so large and so complicated. So they've pretty much only done redundancy on things where the entire mission would fail if they didn't have it. So like they have extra pairs, they have 2 complete sets of nav cams, they have 2 complete sets of HAZ cams on each end of the rover. And I learned something recently. Each of those 2 pairs, one is connected to one computer, the other set is connected to the other computer. So it's not quite as fully redundant as I thought it was. There's like a string of nav cam, forward HAZ cam, rear HAZ cam connected to computer A. And there's another string of nav cam, forward HAZ cam, rear HAZ cam connected to computer B. So if they switch over computers, they switch over to a different set of eyes, which is kind of interesting.
So Kurt Lewis wants to know, why is Mount Sharp so tall? It's taller than the crater rim, but that doesn't make any sense. And you know what? Every time I was reporting on this, I kept having to go, hold on a second here. 5.5 kilometers? Wait, what? No, surely it's 500 meters, or it's 500 feet or something like that. But no. It's a very tall mountain. And it's going to be climbing to the top of this thing. So what's going on? Well,
first of all, it's not going to be climbing to the top, or at least it's very unlikely that they'll choose to do that with the rover, because most of the interesting rocks are in the lower couple kilometers of this. And once you get higher than that, you get to a type of rock that most likely was wind-blown material. So that doesn't tell you about habitable environments, and it's more dusty, so it's more difficult to traverse, more difficult to study with your remote sensing instruments. So as much as I would like to see this rover, at the top of the mountain saying, "Yay, I climbed it," we're probably not going to see that.
Well, and I think there's not a need to climb to the top of mountains to get a good look around anymore.
No,
because
there really isn't.
Now you've got the reconnaissance orbiter overhead helping people map out rocks as small as a wheel. So
right.
I think you're fine.
So anyway, but to get to your question about how can it be possible that there be a mountain in the middle of the crater that is taller than the crater rim itself, I have actually asked this question of a couple of geologists, and they agree that it seems crazy, but there is a story that you can tell that does make some sense. First of all, it's not a central peak. So if you've looked at images of craters on Mars, there's not so many central peaks on Mars, but there's a lot in craters on the Moon and on Mercury. You see, really big craters usually have a central peak in the middle of them. That's not what this is. This is definitely a mound of material that was laid down in layers after the crater formed. And so there's 2 ways you could do that. One is that you could form it as a mound to begin with. So there are some scientists actually initially looking at it with the HRSC camera on Mars Express when that got there, which is about the same time Spirit and Opportunity got to Mars. They said, well, maybe this whole thing is a gigantic spring deposit. and it just kind of built up with hydrothermal deposits and stuff came down the sides. And that hypothesis makes a very specific prediction, which is that if you're building something as a mound by bringing stuff up in the center and it comes down the sides, then you are going to have layers, and this thing has layers, so that's good. But the layers are going to be thicker in the middle, and they're going to get thin as they go to the sides. And that is demonstrably not the case for this particular mound. The layers are continuous. You can see, like, basically you can slice right through the mound that there's this, cap material, and then underneath that there's different kinds of layers, and underneath that there's different kinds of layers. So this thing is layered like this, and the way to do that is to fill the crater. So how can you have a mountain that's taller than the crater if it formed when you filled the crater? Well, the crater used to be taller than that. And also it's quite possible that the fill material overtopped the crater completely. At one time it was completely buried. And there's good evidence for that, because if you look at other craters in the same region of Mars, many of them are filled. Many of them were filled and then partially unburied. So you actually have a lot of craters that have mountains in the middle of them, and several of them have mountains in the middle that are taller than the current rim of the crater. But that rim of the crater that you see right now is a heavily eroded rim. And for whatever reason, the fill material was more resistant to erosion than the crater rim. And it may seem kind of crazy to this idea that you can have several kilometers of fill that then gets eroded away, but it happens on Earth all the time. You look at any place like the Appalachian Mountains or the Colorado Plateau, all of those rocks were once buried several kilometers below the surface of the Earth. Otherwise, they couldn't have formed the particular minerals that they did. So if you have enough time, those kinds of you can have fill and burial and lithification and then exhumation, and the stuff gets eroded away. The crazy thing about Mars that is quite different from Earth is that on Earth we're used to all of this stuff being taken away by water, by river erosion. Water runs against rock, it breaks down the rock, it carries the sediment away, you deposit it in ocean basins. Mars has not lately had that kind of process operating on it. Instead, you have chemical weathering that turns rock into powder in place, and then wind that blows that powder away. And so that's probably what's been happening in Gale Crater. And this process, it's not fast, but it's had more than 3 billion years to operate. And 3 billion years is a really, really long time. It's plenty of time to break down rocks and blow several kilometers worth of rock away.
So I've had the same question a couple of times here, which is from Kurt Lewis and Bob Morrill, which is, if the dunes were not safe, why were they included in the landing ellipse? So you mentioned early on that those dunes, and apparently those dunes were in the landing ellipse.
That's a good question. I think that the landing ellipse contained terrain that they could drive the rover out of. So they looked everywhere for things that would definitely trap the rover. And there were 1 or 2 spots within the ellipse, things like a crater that would be too deep for it to climb out, or a mesa too high for it to climb down off of, or a set of dunes that would entrap the rover and it would have no route out. And the part of the dune field that's in the landing ellipse, they determined that they would be able to get the rover out of it. But they'll not intentionally send the rover into that kind of terrain, but they were confident enough that they could drive the rover out of it that they were willing to include that kind of terrain in the landing ellipse. But that is a good question. I did go to the Mojave Desert a few months ago to see a demonstration of their scarecrow model traversing the dunes, and it was really pretty impressive. They were climbing like a 15-degree dune face, and the wheels were rotating, and it was making progress. It could climb, but there was an awful lot of wheel rotation for the amount of forward progress that it was making.
Yeah, so I mean, that sand is just, I mean, they can get out of it and they can deal with it, but it's definitely not their favorite kind of terrain. So
right, and another thing to keep in mind also is that the ellipse, the rover was not equally likely to land in all parts of the ellipse. The ellipse bounds the region in which the rover was 99.99% likely to land, but it was far more likely to land in the center of the ellipse. And those dunes were toward the edge, so although they appear to cover quite a large area of the ellipse, it actually covered a very small probability of landing within the ellipse. So I think that, in combination with the amount of hazard they saw landing in that particular type of terrain, was a low enough hazard that they decided that it was okay.
Yeah. Okay, we've got a couple more questions here. Now, before I do that, I just want to remind people, if you have questions for us, for Emily, you can ask your questions on Twitter using the hashtag CQX. You can ask your question on YouTube in the comments. You can ask your question on Google+, and we'll be able to sort of gather them all up and watch them. So, and the other thing is we're actually using a new piece of technology today, which is just released for Hangouts on Air, which is the studio quality audio, which should be coming through to you through the Hangout. Now, it's designed for people playing music, but I find that the just the regular voice style of the audio in the Hangouts on Air is not very good. So I'm hoping that it sounds better today than it has been for all of the previous Hangouts. So if anyone can give us a sort of some feedback on whether the audio sounds a little better today than it normally does, that would be fantastic. So, right, okay, so from Gliffery, many of the images sent back mention that they've been treated to bring out features. So what does this involve?
Well, yeah, so when scientists take images using scientific cameras, they're not looking to make pretty pictures. They are looking to figure out something, try to find all the details that they can within them. So there's a variety of things that they may do to process them. One of the more interesting things that they've been doing with Curiosity's images that I have not seen on previous ones is this thing where they white balance the pictures. But actually, I should back up a little bit before I talk about the white balancing, because there's something that makes Curiosity's color cameras practically unique among cameras that have been sent into space. I have to spend a lot of my time explaining how space cameras work to do color imaging. Almost all the time, they have this thing called a filter wheel that has like a red filter, a green filter, a blue filter, a couple of ultraviolet filters, a few infrared filters. And if you want to do color or multispectral imaging, you take one image through one of those filters, you rotate the wheel, you take another image through another of those filters, you rotate the wheel, and then you combine those in post-processing to create color pictures. But there's time separating the red, the green, and the blue. So, like for instance, on Spirit and Opportunity images, if you ever see one of their photos that's in color and you look at a shadow, you'll see little rainbow fringes on the shadow because the shadow actually shifted in the time between the time that they took those three filter images. For the first time, really, in the history of space exploration, a scientific camera instrument has been sent out that operates much more like the camera you might have in your pocket, where it has a charge-coupled device detector that has printed on the detector a pattern of red, green, and blue filter. There's each pixel, there's like a checkerboard pattern where it's one row is red, green, red, green, red, green, red, green. The next row is green, blue, green, blue, green, blue, green, blue. And what you get out of that is every time you take a single snapshot, you can get a color picture. It's just how a consumer digital camera works. And so the pictures that they get back and they put on the web look like pictures that you would get out of your iPhone in terms of the color. And those pictures tend to be very orange because that's what color the light is on Mars. It's sunlight being scattered through an atmosphere that contains a lot of red dust. And so if you were standing there with your iPhone on Mars, you get these reddish colored pictures. What they've been doing with some of the image releases then is they process the pictures by adjusting the pixel values of each of the red, green, and blue channels to look as though it were under Earth-like illumination conditions. So instead of having this faintly pinkish salmon-colored light that you get through Mars's atmosphere, they're coloring it with the sort of with the yellow, or almost what we call white light. Of course, it would look yellow probably to somebody from Mars, or it would look blue to somebody from Mars. And that really radically changes the colors of the rocks. The colors of the rocks originally, they look more red. The soil looks very red. In these white balanced pictures, the rocks look almost blue. And the rocks really are a very cool, dark gray color. They tend to be basaltic. That's what color basalt is. And the dust remains red. And the reason that they're releasing these white balanced images, or the reason that they're producing them in the first place, is because this mission really is packed chock full of field geologists who have a ton of experience walking around Earth and studying the rocks in physical environments outdoors on Earth. And by showing the Mars environment under the same illumination conditions as it would be on Earth, their intuition works better. They look over there, they say, oh, that rock is an unusual color. It might be this sort of rock type. We should go investigate that. And so it's a tool to enable the geologist experienced Earth field geology brains to be able to operate better in the Martian environment.
Yeah, I think it was a pretty smart move to have this kind of a camera on the spacecraft, and I wish they had them on other spacecraft, because I think you're exactly right that the geologists are human beings too, and when you're looking through the kind of raw high-resolution CCD images that come out of these scientific observations, you're seeing a very high-resolution image, but you're not necessarily seeing all of the subtlety and detail. It's only when you use those multiple filters, you build a composite image to actually start to see some of the subtle textures. And so just having nice, like pictures coming out of your DSLR that just look really nice, the geologists are going to be able to spot features and be able to notice textures and be able to use it, not just for science, but also, obviously being able for them to go and right away post all these raw, beautiful pictures out to the public instantaneously, I think has been a huge sort of coup for the public relations, for just getting people really involved and interested in the images that are coming back from Mars. So I think it was a wise move to include that.
Now, one comment that I found interesting, and I actually kind of agree with, from Mike Malin, who's the PI on the Mastcam instrument, he said on the press panel, he said, they got the NavCam images, which are the black and white, more wide-angle view, down from Sol 2, and then they got the Mastcam images, which has this color information. He said on the press panel something to the effect of, I don't think I can see any more information in the color image than I saw in the black and white image. And it's kind of true. If you look at that black and white image, you can see in very crisp detail how different materials that are kind of marching toward the mountain, especially. You go across several different rock types, and in the NavCam images, it's really obvious from their tone, from their brightness or darkness, that you're looking at many different materials. And you see the same thing in the color data. And it's interesting that you didn't really need the color to tell you that, in fact, these materials are different colors. So I suppose that should be some solace to colorblind people. They're actually not missing a whole lot.
And thanks to everybody who gave us some feedback on the audio. That's fantastic. Actually, I'm using the people said that your audio is better than mine, which is funny. Normally, I use a much nicer microphone, but usually the quality of the live hangout is so bad that you can't tell the difference between my good microphone and the bad microphone. But in fact, I think I need to switch back to my good microphone, which is great. So I think this is a big success. So thanks, Google. Right. Okay. So. Remember the picture that you showed way back in the beginning that showed all of the sort of blue sand dunes? Mm-hmm. And so Yoav Landsman asks, the high-rise photo of the landing zone area shows this bluish color. Is that the real color of the rocks or sands? Isn't Mars supposed to be red? So I guess you answered that question, right? It's this dark gray basaltic rock, right?
Right, and so that's an example of an image where it was contrast stretched, and when you stretch each band individually, a color image is made of red, green, and blue channels. And when you stretch each one of those individually so that the darkest pixels are black and the brightest pixels are white, basaltic rock on Mars, which is a very dark, slightly bluish or greenish actually black, that tends to look very blue in comparison to the redder soils. And the reason that they do that is because that way you're taking full advantage of the complete spectrum that your eyes are capable of discerning. If they hadn't done that, it would have been much, much harder to discern the rocket impingement areas near Curiosity, because those would have blended in much closer to the background dirt. So they do that because it helps bring out details that would be invisible otherwise, but I know it does confuse people.
Yeah. So question, this is from Martin Wen, question about the 100mm Mastcam. The only pictures that it's taken are out of focus. Is there an issue, or is it just a matter of adjusting the focus mechanism?
Yeah, both of the Mastcams have focal capability. I think they actually have taken a couple of CalTarget images that were in focus. I think that it's just, I'm not totally sure about that. But these are early images. They're probably just taking very careful steps toward the safe operation of these cameras. So I'm not yet worried about that. If we see over the next several sols nothing but out of focus images coming down, then I'll be worried, but I'm not worried yet.
Like the problems we have with the Hubble Space Telescope. Yeah. Right. But yeah, I mean, in many cases, you're going to see a very deliberate process as they're preparing to use all these instruments. They will, every mechanism that goes on, the focus part is going to be tested separately from the CCD imaging part, which is tested separately from the storage and all of that kind of stuff. And they'll run these instruments through their paces one function at a time and isolate them to make sure that everything is working within its required parameters.
And as far as I know, these are the first focusable cameras sent to the surface of Mars either. And that's one of the things that makes MAHLI, the hand lens imager, so special because, it's designed to have a very, very short, it can focus, I think, within 2.1 centimeters of the surface. That's where it gets its maximum resolution. But it can also focus at infinity. So it's actually the widest angle color imager that the rover has. So it'll be like the dolly camera. They can actually, take movies as they're driving along, showing the landscape, and that'll be kind of exciting too. Actually, I don't know if they're going to do that. I hope they do. When the camera is parked,
so they could take the camera out, aim it at the rover, and then have the rover move along the landscape and capture that as a
That would be bad for arm calibration, so I don't expect to see them actually doing that. But when the arm is stowed, the turret is kind of on the rover's left shoulder, and the camera is kind of staring off to the left. It's a little tilted, but it does have this sort of side view, this view out the window as it's driving along, and I don't see why they couldn't operate the camera in that position.
Yeah, let's put in a request.
Yeah, sure.
Okay, so given that Curiosity does not depend on solar energy, will it make any astronomical observations, like maybe imaging Mars moons from the surface? So sort of sweet chuck pie.
Yeah, I'm sure it will. I'm sure it'll do the same kinds of cool astronomical imaging that Spirit and Opportunity did. Of course, my favorite imaging that they did was astronomical imaging was not done during the night, but was done during the day, when they pointed their neutral density filter covered cameras at the sun as Phobos and Deimos transited the sun. So you see these little dots and a slightly bigger dot in the case of Phobos. Neither one of them looks as large as the sun from the surface of Mars, so it is just a transit. But those are my favorite astronomical observations from the rovers. I'm sure they'll do the same thing. It is you have to be careful when you think about this thing as a nuclear-powered rover. It does still have limitations about whether it can operate at night because the rover is not directly powered by its by the RTG. The RTG fills up a battery, right? And so and you run the rover off the battery. The rover can't do all of its functions all the time off that battery. There isn't enough power for it to do that. So it still has to parcel out its power carefully. The other thing is that because Mars doesn't have a thick atmosphere, the temperature variations over the course of the day are like 80 degrees Celsius. It's huge. And the wheels and most of the motors are wet lubricated. So in order for them to work properly, they have to be warm enough. And so if you try to operate any of those things at night, like the little motors that operate the head of the mast and rotate the mast, those have to be warmed before they can be used, and that takes a lot more power at night than it does during the day. So they still will be quite limited in their activities at night, but I'm confident we'll get some astronomical imaging.
Yeah, I mean it's kind of the same way that Spirit and Opportunity work. I mean they're dedicating a lot of their power to just keeping themselves warm at night, and then they get working during the day when they don't have to focus so much energy on keeping the heaters going. But is there any science that, like actual science, that can get done with Curiosity, or would it just be, like, let's get a picture of the sunset, or let's get a picture of, Earth from the surface of Mars, things like that?
I mean, sunset and sunrise movies are very exciting. The things that they are most interested in overnight really are weather observations, and so they're very curious about the wind patterns at night, clouds at night. Also, there are certain instruments that are better to operate at night. So like, I think it's the APXS, works better at cooler temperatures. So there are certain things that they will want to be doing at night. So there are good reasons to be awake at night. It's just that they can't do as much as they can during the day. And they certainly won't drive at night.
Yeah, but I'm just spitballing, but I can imagine that they're sort of atmospheric. You're going to want to, look at the sky at night to sort of see some atmospheric effects from the surface of the planet, and there might be value to some of that. So I'm not sure what their plans are for that. So now it's 5 o'clock. I don't know, how much time do you want to
I can maybe take another 10 more minutes, but then I probably ought to go.
Okay, let's do that.
I have a couple of questions from my blog comments, so let me bring a couple of those in. One is a simple one, which is, do you know when we'll finally see the top of Mount Sharp? And many of you probably have looked at the Mastcam panorama and been a little bit frustrated that they didn't quite aim it high enough to get the top of the mountain. And the reason for that is because that whole sequence was planned before the rover landed. They knew that Mount Sharp was going to be taller than their field of view, but they didn't know where it was going to be. And so there wasn't really a good way for them to sequence that and tell the rover which images to return before they landed. And so they did their best, but they didn't get the top of the mountain. I understand that this week, actually, within either today or tomorrow, they will be taking a new Mastcam set of images that should show the top of the mountain, and then we can hope to see those back on Earth in another couple of days. So hopefully by the end of this week, we will be seeing the top of Mount Sharp. Another question. Oh my goodness. There's somebody who posted 40 questions. A pro tip, ask one or two, and then I'm more likely to answer them. And so actually, you go ahead, Fraser, if you've got another couple of them.
Sure. So Hector Katz wants to know, is there sound on Mars? Yes. But is there a mic on the spacecraft?
There isn't, and the Planetary Society is extremely chagrined about this because we have been trying to land a microphone on the surface of Mars since there have been things landing on the surface of Mars. And one thing after another, we actually had one on Mars Polar Lander, and we know what happened to that mission. There was a microphone on the descent imager on Phoenix. Because and it was for a weird reason. It wasn't our microphone. It was because Phoenix used the descent imager used an off-the-shelf cell phone camera detector that the chip happened to include a microphone. So they're like, why the hell not? And so that it could have been used, but it wasn't because that mission was just so much on a shoestring and they had so little time to operate. So they never did use that microphone, sadly. We tried to get it on this spacecraft. They said, our spacecraft is already complicated enough. Thank you. We don't want it. And so we're hoping...
See the point.
Yeah, so then the next mission, actually, that could possibly carry it is a discovery mission called InSight. It's one of 3 discovery proposals currently under consideration by NASA. The other 2 are, so that one's a Mars lander. There is a Comet Nucleus lander, and there is a Titan Lake Explorer. All of these sound really thrilling. So while I would love to have the microphone be on the Mars lander, I would equally love to see a boat sailing around Titan. So I really don't know which discovery mission I want to win. But that selection is going to be announced within the next couple of weeks. So stay tuned for that.
That would be awesome. A boat
Titan
sailing
boat.
around Titan. Yeah. But no, I mean, I think that I know that question hits very close to home because I know that the Planetary Society has been lobbying and trying to organize.
We have flight qualified hardware.
Microphones for the surface of Mars. This has been, one of your primary, that and solar sails.
Yeah.
So okay, so let's get a few more questions here.
Oh, this doesn't bode well.
So Fearless Thinker wants to know, what will MSL do with the material it has already processed with the SAM and Kemin? Does it go to the bathroom?
Actually, I have not asked the question in that way before, but it must. It has to.
Isn't that the perfect way to describe it?
It is. We've anthropomorphized this rover enough already, but that is something that I'm going to have to follow up on.
How does it do that? Does it, does it just drop it on the ground underneath? Does it scoop it back out and brush it out? Does it create some kind of owl pellet and
I really don't know.
Regurgitate it back out. What is it? How does it get rid of the material it's studied?
As far as I recall, the belly pan is flat and featureless, so I don't think it just craps it out the bottom. There's got to be some other method of ejecting it. I don't know if there may be some kind of container within the rover that it just goes into. I don't know.
Does it pack it back out again?
That's exactly, yeah. Pack in, pack out. I'm gonna have to follow that one up. That's a fun question.
Yeah. I'm gonna give that story to Nancy. It's a race now.
Definitely.
Okay. Let's see if we have any more. Okay, so do you think there would be any findings? So this is from, I can't even say this Twitter handle. Altoid Yoda. Okay, I got it. Are there any findings in particular, short of a fossil, that could excite Congress enough to finally okay a human mission?
Well, I don't know. I don't know what we could find that would excite Congress other than like a Chinese flag on the surface of Mars. But I think that
I don't think that would even do the trick.
One of the things that one of the more exciting things that Curiosity will be looking at is actually about the present environment on Mars. And that's this question that's going to be following up on the possible detection of methane in Mars's atmosphere. That detection has been made from Earth, and there are some people who are very excited about it, but you have to remember that when you're detecting methane on another planet from Earth, you're looking through an atmosphere that also contains methane. That's okay when you're talking about like Uranus and Neptune because they have a lot of methane, so the signal is really clear. But for Mars, where the amounts are very small and transient, it's a little bit more difficult to be confident. But Curiosity will be able to detect it if it's there. And even more cool is that it will be able to study the isotopic ratios of the carbon and of the carbon inside that methane. And, if those are out of kilter from what we expect, that could mean something very exciting about, life processing it beneath the surface. Although that's one of those things where extraordinary claims require extraordinary evidence. It would be interesting and suggestive, but you won't see scientists shouting, "We've discovered life from the rooftops." Although their press officers may, so I don't know.
Yeah, exactly. They might give you that impression. But I guess there's enough interest in the public space, I think, that a human mission to Mars now is feeling a little more inevitable. I don't know if you saw Elon Musk's presentation at the Mars Society a couple of weeks ago, and he said, "I'm sending humans to Mars in 15 years. Won't be that expensive. We'll have the spacecraft to do it. Thanks for paying for its development, NASA. This is all going to happen now." So, if there's anyone to believe, I think Elon Musk is a pretty good guy to believe at this point. So I think whether it's going to be Congress voting on it, whether it's going to be a Chinese flag on the Martian soil, as you say, whether it's going to be an international group, whether it's going to be, I keep seeing Russian plans to send humans to Mars that never seem to pan out. Or Elon
I would
Musk.
not get on that rocket. But I'll tell you, and this is personal opinion. This is not Planetary Society opinion. But I look at the writing on the wall, and I don't believe that NASA is going to be the first ones to send humans to the surface of Mars. I think it'll be a private company because they'll do it much cheaper. They're willing to take on much more risk, and they will send people who aren't interested in coming back.
Yes.
And really, the difficult thing about a human mission to Mars launched by NASA is that they would be determined to bring people back, and that's really hard. But if you don't intend to come back, which NASA won't do, but private companies certainly will. I would not be surprised to see Elon boarding his own spacecraft to go retire on Mars, like he said he wanted to do. So that's what I think. If we see humans on Mars in 15 years, it'll be humans who do not plan to return to Earth.
Yes, yeah, we did an article on Universe Today about that the most logical mission is a one-way, one-person mission to Mars. Send a bunch of cargo, send a human, a few years later send someone else, and then, assume that 20, 30 years down the road there's going to be a way to get back. So I think that's great. Well, I think we're out of time then. So it was fantastic to hear you talk about Curiosity. Wow, it is really exciting. And
it is very exciting.
It is, and the best is yet to come. I mean, it hasn't even moved yet.
Yeah. It hasn't really done anything yet, so we've got a lot to look forward to. Especially that I cannot wait till it starts climbing in among those dunes. It's going to look like I don't know, Alderaan or something. It's going to be really exciting.
And I think it will climb to the top of that mountain. Once they get through the first part, then they'll be like, well, where are we going to climb back down? No,
they're gonna flank it because you go around the mountain, you get to very different rock types. So.
Okay.
Talking to your kids, Fraser.
Yes.
I recognize that.
Can you tell? Yeah. Well, then why don't we wrap this up? So, well, you know what? Wait a minute. This is your hangout. I'm just.
That's true. You're not the host anymore. So that's right.
I'm just going to get back and let you wrap this up.
You're my lovely assistant, Fraser. So thank you very much, Fraser Kane of Universe Today, for helping me out on today's Hangout. I am Emily Lakdawalla of the Planetary Society, which, may I remind you all who are still watching, is a membership organization. You can go to our homepage and join for the low price of $30, and you will be supporting space exploration, being part of tens of thousands of people around the world who are advocating for more space research and exploration. And, of course, you'll be supporting me, Emily Lakdawalla, who blogs at planetary.org/blogs every day. And I hope to see you. I plan to do these at least every other week, and I might start doing them more often, actually, because this has been an awful lot of fun. So thanks again, Fraser. Thanks to all of you observing, watching today, and I'll see you next time.
All right. Thanks a lot.